Okay, welcome to the video for 2.3 polynomial functions of higher degrees. So after this section, you will be able to graph a polynomial function of higher degree as well as use these functions to model real-world situations. In this video, we're just going to work on the graphing here. All right, so what do we know about the graph of a polynomial function of n degree? Well, it's really what I know, and I'm going to now share with you. Okay, it has at most, so operative words here, at most, n number of real, this is also important, real zeros, and it has at most n minus 1 local extrema, so max or min. So I'm saying real zeros because we're going to get into imaginary zeros or complex zeros eventually, but at most, real zeros where it crosses the x-axis. So for instance, let's say we have a polynomial and it's x cubed, okay, but there's more to it. Poly means multi, so there's other terms here. It's not just a single term polynomial. It can look like this. Here's an example of what it could look. It could look like a whole bunch of things, but I'm going to just show you a couple of examples here. So it could look like this. It could also look like this. And what I want to show you here is since the degree is 3, the most number of zeros it could possibly have is 3. In this case, it has 1. But in this case, it has 1, 2, 3. And then it has at most n minus 1 local extrema. So we're talking about degree n. In this case, we're talking about the third degree. So it has at most, for this one, 2 extremas. And so you can see them here. There's one here, and there's one here. There are none in this case, but it couldn't possibly have any more bumps than what it has here because we have x to the power of 3. Okay, if we know that what the lead term of a polynomial is, we can also determine the end behavior. So that's going to help us graph these. So let's go down this little chart here. So if the lead term is positive and the degree is even, well, I'm going to give you an example of the most popular one we know, but it's going to work for all even ones. Well, the one that we're most familiar with, and it holds true for this one, is x squared. Right, and x squared looks like this. So when the lead term is positive, our left end is approaching infinity and our right end is approaching infinity. When it's negative, when this is negative here, it flips upside down. So now we're just going down like this. So this isn't really new information. We're just broadening it to have to do with higher degree polynomials. So we're talking about any polynomial that starts with x to the power of 4, x to the power of 6, x to the power of 8, anything that has an even degree. All right, so following that, let's give you the example of x cubed, because we're all familiar with x cubed. Well, when it's positive, it looks like this. So our left end is going to approach negative infinity, and our right end is going to approach positive infinity. And then when we put a negative out here, we're going to flip it, and we're going to have the opposite. So we're approaching positive on the left end and negative on the right end. In a moment, we're going to pull all these things together. But first, let me tell you about multiplicity. Okay, in kind of simple terms, multiplicity just means how many times a certain number is a zero for a polynomial. Okay, so that's kind of a very basic way of saying it. It might be a little confusing, so let me give you an example here. If I have the factored polynomial, let's see, x minus 3 to the power of 4 times x minus 5 times x minus 8. To the power of 2. Okay, we have 3 zeros here. That's a 5. It looks kind of smushed up there, but that is a 5. So let's list our zeros. We have the following zeros. We have 3, we have 5, and we have 8. And I'm leaving some space here. The multiplicity for each zero, well, for the 3, the multiplicity is 4, so it has a multiplicity of 4. For the 5, the multiplicity, well, if there's nothing up here, that's just going to be 1. It has a multiplicity of 1. And for the 8, we have a multiplicity of 2. Okay, so now what does that mean, or why do we need to know that? Well, that is how the graph is going to behave at these zeros. So when we have an odd multiplicity, it's going to go through. So go through the 0. Okay, again, our most famous one, when we think of this, there's at x cubed, there's a 0 at x, well, it's going through, as opposed to the even multiplicity on x squared where there's a 0, it does not go through it, it bounces, so bounces at the 0. So in this case, if we were to graph this, at 3, since it's even, think to yourself, is it going to bounce or go through? Well, if 3 is even, it is going to bounce for this one. This one, 1 is odd, so it's going to go through. And this one, it's going to bounce. All right, so let's bring this all together and graph one. So I've broken it down into steps for you. So here we have this. Determine the degree and sign of the lead term of the function so you know the end behavior. Sketch that on the graph. All right, so the sign, well, if we take all these x's, they're all positive. They're all going to multiply together. So the sign's going to be positive. So sign positive. Well, what about the degree? And I'm going to do a little quick demonstration for you. You don't have to copy this down, but I want you to understand how to come up with the degree here. And you don't have to copy this down. I'm just giving myself some space to do this. All right, so if I have this problem, if I were to find out what the degree is, that's when I multiply all this together. So I would have x minus 3. And then when I square this one, I don't just distribute that 2. I actually have to square that binomial. And so in the next line, I would have this, and then I'd have to multiply this and this together. And so the first time I do that, I'd have x cubed. Right, so I'd multiply this and this and this and this, and I'd have the rest of it. And then I would still have to multiply all that, whatever it is, times x plus 4. Well, when I multiply these together, I'd have x to the power of 4. So all I really need to do here is add up all the exponents. So this is 1, this is 1, 2 plus 1 plus 1 does give me 4. So coming back over here, we're just going to add up the exponents. 2 plus 1 plus 1 is 4. All right, so then it says sketch that on the graph. So we know it's positive, so it's gonna, and it's a degree 4. Well, this is even. That's the important thing to pull from this. So we're going up and up like that. And we don't need more information than that at this point. All right, place a point at each of the zeros, also known as roots. So where do I have my zeros? Well, I have a 0 at 3, I have a 0 at -1, and I have a 0 at -4. So I'm going to go ahead and place points there. So at 3, -1, and -4. And then starting with the left, sketch the graph as it hits each 0, being sure to mind the multiplicity of each 0, and if it bounces, I'm missing a part here, or goes through the 0. Okay, so I'm starting from the left. Well, at negative, actually, let's just make a little list here. So 3 has a multiplicity of 1, so that means it's going to go through. -1 has a multiplicity of 2, even, it's going to bounce. And -4, odd, go through. Okay, so now I'm just going to follow this along. Well, I'm going to approach -4 first. It says go through. So I'm going to go through. And -1, I'm going to bounce. And then I'm going to go through. Okay, a couple things to notice here. If you do your multiplicity wrong, then you're not going to match up. You're not going to meet up with the arrows that you originally drew in step 1. So you'll know that there's something wrong in either what you did in step 1 or in your multiplicity, and you'll have to go back and fix it. Next thing, it doesn't look exactly like this here. Okay, it's not just going right like that. It probably is a lot steeper. For now, what you would have to do is find out you'd plug in these numbers to find some other points to graph it more exactly. I'm not asking you to do that right now. Right now, all I want you to do is get a basic shape of the graph. We could find the y-intercept and get this a lot more exact, but I just want to see that you know where it bounces, where it goes through, and what the end behavior is. All right, let's do another problem together. Oh, there's the little piece that I was missing there. I'll fix that in your notes. All right, graph the following equation. All right, so starting off, we need the degree. So the highest degree, so degree 4, so even, and it's positive. All right, so once again, positive, we're going to be doing this one. And now we need our zeros. Well, this one is not factored, so guess what we have to do? We have to factor to find zeros. And you have to think way back to factoring. Remember, the first thing you want to do when you factor is factor out any greatest common factors. So I'm just going to copy my function down here. What do I see is in all of them? Well, I see there's an x in all of them, and the lowest degree is 2. So I'm going to factor out an x squared. So factor out an x squared, and then I divide through, and I have x squared plus 8x plus 16. All right, I need to keep factoring. So if I'm moving down, I actually recognize this as a perfect square trinomial. I'm just going to go ahead and factor it as such. Okay, now I have my zeros. I have a 0 that is going to bounce. And I have a -4 that is also going to bounce. So it's 0 and -1, 2, 3, 4. And you don't have to connect with this. You could erase that if you wanted. But you're going to come down, bounce, bounce, and go back up. Bounce, bounce, and up. And that just reminds us where we're starting, and hopefully we end up where we should end up. Okay, I've left 4 for you to try. We're going to take a look at them in class. 2 are already factored, 2 are not. So you're going to have to practice that factoring. All right, thanks for watching, and I will see you in class.